little over 80 centimeters. We nailed that.
Yeah, I was hearing like it seems like it's getting, the sound is getting lower, it was getting faint as it was going down.
Yeah, it gets a lot harder. The one big drawback to this experiment is, depending on the frequency, that sometimes it's really difficult to catch the next harmonic, and especially if you're in a room with other people doing the same thing, you know, you're hearing it getting louder, but it's someone across the room. And so it's really convenient to do this lab when there's not many other people around, so people go in the hallway or another room.
Is this known as Hooke's Law?
No, this is not Hooke's Law.
What is Hooke's Law?
Hooke's Law deals with as the stretch increases, the force increases. So I got a slinky here. As I pull down on it, the force required to pull the slinky down, or the force that the slinky exerts back on my hand, increases the farther I go. And the fact that it's linear is, if I double the distance of the stretch, the amount of force doubles. That's Hooke's Law. All right. Yeah, higher frequencies, I don't have to go down as far. The other issue with this is that there are false harmonics. So it's the one lab, you really should not do this as a general practice of figuring out what the answer is and then seeing if you can get to it. This is the one exception to that, because let's see if we can actually get that. So the main harmonic was somewhere around here.
So when you hit it, the water's going up?
That's the first harmonic. Sorry, too quiet. Got a little bit louder right there. Or maybe this is the, you know, it's a physics demonstration. It's a, yeah, it's just not gonna do it. If you start at the top and you start working your way down, there's another place where it gets a little bit louder. So it might go, and then when you get to the harmonic, it's even louder. But if you miss where the first harmonic is, that completely disrupts all the rest of your calculations. And so it's really cool when it works. All right, the last one, we've done the 2 fixed ends, we've done the 1 fixed, 1 free, 2 free ends. And when you think free ends, you should be thinking antinodes. And then we're going back to the first harmonic, second harmonic, third harmonic. So first harmonic, basically that. That's the simplest pattern. So the question is, how many waves is this?
What? It's not even a wave, or.
Would
looks
be
like a
1 or
flutter.
2 halves. It's like it's,
No, it's not 2 halves, but remember, that's a whole one right there.
The whole one,
oh.
Right?
remember a whole one looks like that.
Is it 2 fourths?
It's yet better drawn. So what is this one?
Could be a half?
It is a half. You basically have chopped off the quarters at the end. So half of the wavelength is equal to whatever that length right there. The next harmonic, the second harmonic, and as before, you add a half wave every single time. So if the first one was a half wave, how much is the second one?
That looks like that.
3/4?
I thought somebody else said it, it's not 3/4,
One.
1. You had a half wave every single time, so if I have a half wave and I add a half, I got 1 now.
Oh.
The next harmonic would be how many waves?
No? It looked like one way.
That is 1 wave. Next one,
1.5?
1.5, or 3/4,
You said the next
or
one.
3 halves.
Sorry.
So in the first one, the length is, sorry, try that one again. The wavelength is 2 times L. The next one, the wavelength is equal to L. The next one, the wavelength is equal to 2/3 L. We went to the next one.
Excuse me, yeah.
So that would be 2 waves. Oh, oops, that's my problem. That's the third harmonic. And then first, second, third, yeah, fourth harmonic. Yeah, we're adding the antinote each time,
Oh my goodness.
so that's 2 waves, or the length is equal to half. And made that mistake several times. There we go. The wavelength is half of whatever the distance is from end to end. So we can make predictions now. That's actually the second harmonic, I believe. I usually use a different tube, but I'm pretty sure that's the second harmonic. Third, fourth,
So cool.
and hit a fifth up there.
Mister, you don't never want to let me take nothing home to my kids to play with.
Oh,
Oh.
I think you would never want to take that home to your kids.
I was like, no, I don't want it, I don't want it anywhere, I was just kidding.
Do you know what a bubble ball is? Anyone have one as a kid or have one for? It was really cool. The first time we ever saw one, our son was still I don't know if he was walking yet. So we got one of those for him. And it's really cool when he has it holding it and holding onto it like this and his little chubby cheeks were shaking. But at some point, you're just praying for the batteries to die. All right, so let's predict.
So wait a minute, Mr. So we got the last one that said that that's 2 waves. That's 2 wavelengths down at the bottom.
Right.
And you said the length is 1/2? Is half?
So L, being the distance from end to end,
Uh-huh,
is 2 wavelengths.
yeah.
So therefore, a wavelength is just half of that length. There's no- That's 1 wave right there, that's another wave right there.
I know that, I know what you were saying. Okay,
It's like a calculus trick.
he was trying to use, yeah.
All right, so first off, to make predictions, we need to know what the length is. Now, the other one, it's cut off at some point, and I don't have this thing there. You know what, it's a physics demonstration, like it's gonna be perfect. I'm going to assume that the node is happening right there before we get to the cup. So basically, I want the length from there, I want that length right there, from this end to that end. And it's just onto the meter stick, and it's coming out at about 82.2 centimeters. Now I stretched it a little bit, because as you swing it, it will stretch some. The faster I swing it, the more it will stretch, and so that length is not a constant, but it's close enough. It's not gonna stretch significantly, I hope. And we wanna use the international standard units, so meters. So centimeters to meters, how many places do we move the decimal point?
2,
So 0.822 meters. The first harmonic happens at twice that, so when the wavelength is 2 times L. So the first harmonic, the wavelength is 2 times that, 0.822. .644 meters. But we're trying to figure out what is the frequency that we would hear. We'll tell you,
Where did we get 1.644 from?
2 times that.
Smart.
I know the speed of the wave is frequency times wavelength. So the speed, it's sound we're hearing, so 343 meters per second, is equal to the frequency, which is what we're trying to find, times the wavelength of the first harmonic. The math problem we're working with here is 343 is equal to 1.644 times the frequency. That's the math problem.
And the question is, what is the frequency of the wavelength?
Yeah, for the first harmonic, what frequency should we hear? Now, for the other one, I'm pretty sure this is gonna be the same here. We actually aren't gonna hear the first harmonic. We'll come in at the second harmonic. Because ultimately what's going on, the end down here where my hand is not moving particularly fast. This end is moving significantly faster. Because this end is moving faster, there's less pressure here. Therefore, sound is getting sucked up through the tube. As sound comes up through the tube and hits the ridges right there, the air will start to vibrate. And if you are swinging at just the right speed or within the certain region, you will start to hear harmonics. You get the standing waves where the antinode at each end. In theory, if I'm on the first harmonic, it should be silent in the middle. Unfortunately, if we put a device in there to measure it, we mess up the tube and we shouldn't be getting it anymore. So we have to have some faith that it's there. So anyway, what is the frequency we are predicting?
I had 208.63, I think.
208.63?
And that was because I divided?
Yep.
Okay.
343 by 1.644. And units?
Seconds.
Not for frequency.
Hertz.
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 You could have said 1/seconds and that would have been fine. Hertz.
Are we ever gonna need to use kilohertz?
Kilohertz.
I have not used it before in this class, but. So now let's find out what exactly is 208.63 hertz. What will that sound like? Oh yeah, I forgot how slow this thing is. All right, so while that's waiting for the internet to actually connect, let's predict what the second harmonic is going to sound like. So it's a very similar process to what we just did. Second harmonic, the wavelength and the length of the tube should be the same. So for the second harmonic, the wavelength should be 0.822 meters. The frequency is just going to be the speed divided by that wavelength, 0.822. And 417.26 ish.
Oh, sorry. Did you say 417?
0.26?
Yeah.
Good. It's basically, I just doubled that. Is it up yet? Yes, it is. All right, that's 440 hertz.
Okay.
The other one was 208.63. That's the first harmonic. That's what we're predicting. Let's see if we hear it. Yeah, we nailed that. The trouble is, I have to swing it so slowly, there's not enough pressure difference to get air coming through with the right enough speed for us to be able to hear it. It's not gonna be loud enough. So that's the second harmonic. So let's figure out, we have predicted what the second harmonic should be, 417.26.
I spent like 15 minutes going over. We should have done what we talked about.
That's the second harmonic.
Swing that thing at the same time.
Say it again?
You should swing the thing at the same time.
Yeah, that's super close. All right, now the question is, how close is it? How can you tell? Well, let me play two frequencies using the computer as opposed to having to rely on my swinging that thing. All right, so here's 440 hertz with speakers on. All right, so that's 440 hertz. I'm now going to play 439 hertz. .439, 440. Could you hear a difference in frequency?
A little bit.
And occasionally I have students who have really well-trained ears. A couple of you are thinking you heard the difference, or heard the difference. And so I cannot tell the difference, but some people can. If I play them at the same time though, hopefully you definitely heard some oscillation right there. So what I did is I took two different frequencies. One's in purple and one's in blue. Now, at a quick glance, perhaps you don't see that there's a difference between these. There is a subtle difference. They both start at the same place at 0, 0, but they end slightly differently. The purple one ends just after bottoming out, just after the trough, and the top one ends on the way down. So there's a very subtle difference. I'm hoping that you can see that there is. I then took the blue one and I traced it onto here. So if I put the purple one inside this, wrong way. And I'm making sure that they line up at the beginning where, so they start in exactly the same spot. Hopefully you can notice that over time that they start getting more and more out of sync. So we start out with definitely constructive interference because they both peak at the trough at the same time, but at this point, we potentially are getting destructive interference. So they start out in sync and then they get more and more out of sync as you go, because the frequencies are just slightly off of each other. If you add them together, and I am going to point out, not necessarily trust your eagle eyes for this, that it goes from 1 to -1. We have an amplitude of 1 here, so from the middle to the peak is 1. When I add them together, they are now peaking closer to 2. So this is going from -2 to 2. And notice that the peak here is getting less and less as they start to become, never quite become completely destructive as far as the peaks go, because we're still above 1, but we are getting smaller and smaller. If I extend that out even more cycles there, we get this. This is the dead spot right here, and this is where it's the loudest. The bigger frequent difference in pressure coming from the sound, the more eardrums get popped in and out, the louder we hear it, and then at this point it's quiet. So that's why you get the whoa, whoa sound. Now the math involved in this, because there's a frequency here, the amplitude changing has a frequency. It's as if you're modulating the amplitude, as in AM radio is amplitude modulation, as opposed to FM, which is frequency modulation. So when I was playing the 440 hertz, and I played the 439 hertz, there's a frequency that comes on top of it called the beat frequency. And here's the sophisticated math. Right there. So since the beat frequency is 1 hertz, to find the period, because we're going to time it, the period is just 1 over that, and this marker's getting worse and worse. This will show up better. The period is 1 over the frequency, or 1 over 1 hertz, or 1 second. So this would predict that it should get quiet every second. Let's find out if that works. Too loud there. 1001, 1001, 1001, 1001. We can get them closer. So if I play 440 and 439.5, well, let's predict it before we actually